Imagine this. You're standing outside on a clear night, no clouds, no city lights, just you and the universe. You look up, and for a moment, everything feels massive, not a little big. Not hard to imagine. I mean cosmically, brain-bendingly, incomprehensibly huge. And then it hits you with all those galaxies, all those stars, all those planets. Is it really possible that we're the only ones? It almost feels arrogant, doesn't it? For thousands of years, humans have asked the same question. Are we alone? Well, today, we are closer to an answer than ever before. And the journey to get there is one of the most fascinating, bizarre, hopeful, and sometimes terrifying scientific adventures humanity has ever taken. This is beyond Earth, and today, we're going to explore why the universe is silent, why it might not be, and what that means for our future on this pale blue dot. Strap in. Let's get cosmic. Alright, let's start with something simple. Or actually, not simple at all. The universe, the whole thing is about 93 billion light years across, and that's just the observable universe. The part we can't see, that's probably much, much bigger. Now, in that space, we have an estimated 2 trillion galaxies, each with billions of stars, and most of those stars have planets. If we made a list of all the places where life could emerge, that list would be, well, bigger than anything your computer could store. Life seems probable. And that brings us to the cosmic mystery of all mysteries, the Fermi paradox. In the 1950s, physicist Enrico Fermi asked a simple question: where is everybody? If life is so likely, if civilizations can arise, if the universe had billions of years of a head start before Earth even existed, then why don't we see anything? No alien signals, no megastructures, no star systems going dark, no evidence of interstellar expansions. Just silence. And the silence is loud. But here's the thing, silence does not mean emptiness. It might mean mystery. It might mean distance. It might mean something is blocking us from hearing. Or it might mean we're looking in the wrong way entirely. Today we're going to break all that down, and trust me, by the end, the silence will feel very different. Okay, let's talk about Goldilocks, not the porridge girl. The Goldilocks zone, the not too hot, not too cold region around a star where liquid water can exist. For decades, scientists thought a planet just needed to be in that zone to be habitable. Simple, right? Actually, not even close. Today, the concept has exploded into a multi-layered checklist of cosmic requirements. First, the star matters. Your host star can't be too young, too old, too massive, or too small. It's like the universe's version of Tinder the star has to match the planet's vibe. Most promising stars? K-type dwarfs, long-lived, stable, orange-colored stars. Our sun? Pretty good, but almost on the short end of the lifespan scale. Second, the planet needs more than water. Sure, water is essential, but what else? A magnetic field to block radiation, a stable climate, plate tectonics to recycle carbon, a long-lived atmosphere, and chemistry that supports complex molecules. Earth didn't just win the lottery, it won every single ticket in the machine. But here's the kicker. We're finding planets everywhere now. Thanks to telescopes like Kepler, TESS, and the James Webb Space Telescope, we know that 1 in 5 Sun-like stars likely has an Earth-sized planet in its habitable zone. There are likely 40 billion potentially habitable worlds in our galaxy alone. 40 billion Earth-ish planets. Just in the Milky Way, that changes things. And get this, we've already found some very intriguing candidates. Planets like TRAPPIST-1e, almost Earth's twin. Kepler 452b, called Earth's cousin. And K218b, which might have water vapor in its atmosphere. Are these worlds alive? We don't know. But for the first time in human history, we have the tools to find out. Let's rewind the clock, way back, 4 billion years back. Earth was young, messy, volcanic, unstable like a teenager who hasn't figured out their identity yet. And somehow, in that chaos, life emerged. Not fish, not trees, not dinosaurs. No, something unimaginably tiny. Microbes. And that alone took hundreds of millions of years. So here's something your high school biology textbook probably didn't tell you. Life might be common. But complex life? That might be incredibly rare. Let's run through the evolutionary level-up steps Earth went through that many planets might never reach. First, abiogenesis. How do simple molecules become living cells? We still don't know exactly, but we have clues: hydrothermal vents, lightning-charged chemical soups, or meteor-delivered building blocks. It's messy, chaotic chemistry that somehow woke up. Then, photosynthesis. Life learns to harvest sunlight. This changes everything, turning Earth's atmosphere oxygen-rich, a rare, explosive biological transformation. Next, multicellularity. Cells team up, specialize, and form organisms. This is not automatic. It took 2.5 billion years to happen on Earth. Many planets might stall here. Finally, complex brains. Intelligence doesn't just show up. It requires stability, time, and evolutionary pressure. Octopuses and dolphins came close, but only humans crossed the final threshold. The point? Intelligent life might be the exception, not the rule. But if even one planet out of billions produces intelligence, that's enough. Because intelligence changes everything. Okay, so at this point you might be thinking, alright, we've got billions of habitable planets. The ingredients for life are everywhere, and evolution had plenty of time to do its thing. So where are all the aliens? This is where we enter one of the most intellectually thrilling and possibly terrifying ideas in all of science: the Great Filter. A great filter is an event, a barrier, a cosmic choke point that stops life from progressing to advanced spacefaring civilizations. Think of evolution like a video game with levels. The Great Filter is the level where almost everyone fails. But here's the biggest question in all of astrobiology. Is the Great Filter behind us or ahead of us? Let's explore both possibilities. First, a Great Filter behind us. This is the optimistic scenario. It means the hardest steps in evolution have already happened on Earth, and they're extremely unlikely elsewhere. Candidates include abiogenesis, the jump from chemistry to biology might be a once-in-a-universe miracle. Or complex cells, which came from a freak fusion event scientists call the lucky accident that made animals possible. If these steps are exceptionally rare, the good news is, we're special. The bad news, we're alone. The other option is a great filter ahead of us. This is the pessimistic scenario, but many scientists argue it's more likely. If the universe is quiet, maybe lots of civilizations reach a certain level and then wipe themselves out. Possible future filters include self-destruction, climate instability, or even runaway artificial intelligence. It's humbling, it's disturbing, and it's also deeply motivating. Because whether the Great Filter lies behind us or ahead, the silence of the cosmos means something. We just don't yet know what. Alright, time for the fun part. Let's look at some of the most mysterious signals we've ever detected. Do any of them prove aliens exist? No, but they are weird, exciting, and in some cases still unexplained. First, the WOW signal from 1977. This is the big one. An astronomer saw an incredibly strong 72-second signal coming from the constellation Sagittarius. He circled the printout and wrote one word in the margin: wow. We've never heard anything like it since. No natural source fits perfectly. To this day, it's the closest thing to a possible alien broadcast. Just that one cosmic ping. Then there's Tabby's star, the alien megastructure star. In 2015, astronomers noticed it would dim irregularly by up to 22%. The strangest hypothesis went viral. What if it's a Dyson sphere being built around the star? A massive alien megastructure. Spoiler, it's likely dust. But for a few glorious years, the world got to ask, what if? We also have fast radio bursts, or FRBs. These are millisecond-long cosmic flashes that release more energy than the sun produces in days. Most are likely natural, but a few are strange enough to keep scientists awake at night. The search is getting better, more sensitive. We're learning to hear whispers in the cosmic static. So how do we search today? The James Webb Space Telescope is a game-changer. It can detect methane, carbon dioxide, water vapor, and even possible industrial pollutants in the atmospheres of distant planets. Meaning if an alien civilization is out there smogging up their skies like 21st century humans, JWST might catch them. Within the next decade, we might get the first confirmed detection of life-friendly atmospheric chemistry. That would be one of the biggest moments in human history. And of course there's SETI's search for extraterrestrial intelligence. It's like the universe's biggest listening station scanning millions of stars for radio signals, laser pulses, or infrared signatures of alien megastructures. Today, humanity is crowdsourcing the hunt for alien life, with volunteers around the world lending their computer power to the search. Then there's Breakthrough Listen, the largest SETI project ever created. It scans 1 million nearby stars and 100 nearby galaxies. Every single second it watches for a cosmic hello. We haven't found one, Not yet, but we're listening harder than ever. Thanks for watching. If you're as fascinated by this as I am, be sure to subscribe for more journeys beyond Earth, with the weird and unexplained, with John.